Hey guys, so before we get started today, just like with the science lesson, I just wanted to say thank you to all of you. Um, it's been a really great experience being your math teacher this year, and for a couple of you, a portion of last year as well. Um, yeah, I mean, I hope you guys have enjoyed the classes that we've had. I know for some of you that the material that we covered was a little bit advanced, so I get that it was stressful or not so enjoyable at times. But my goal with this school year was to show you some of the things that you'll need, some of the tools that you'll need if you decide to sort of pursue a career that involves like high school math. Last year it was a similar story, but I went all the way up to first year university math, um, just because of how the timing worked out. That was something that I was able to do last year. But this year we went at a little bit of a slower pace, so we covered topics in greater detail. But I hope you guys found it useful to go uh, through so many different kind of levels of difficulty. We started with, if you guys remember back in September, we started with those multiplication tables. That's like stuff that I used to do when I was like 8, 9, 10 years old in school, that we would have those kinds of mad minute contests. And then we are finishing now with trigonometry, which is grade 11, so something that I would have been doing when I was 16. So we covered now, we didn't cover everything in between, but we did cover stuff ranging across a very large number of grades. And that was kind of my goal, was to give you guys a taste of, grade 9 math, which was linear functions, grade 10 math, which was quadratics, grade 11 math, which was trigonometry. And if you guys want more videos, I can try to make more videos through your summer. But basically, the continuation of that, grade 12 videos would be or rather grade 12 lessons in these video forms would be like the introduction to calculus, or working with, instead of quadratics, which is x squared, you'd be working with cubic functions that are x cubed, or quartic functions, x to the power 4. Things like that. So grade 12 works with those things and like how to factor those kinds of things, and then gets started on calculus and vectors. So if you guys want something like that, let me know, and whenever I have the time, I'll put something out. But yeah, otherwise it's been a really great experience being your teacher, and I just wanted to say thank you guys for being such a great group of students. Also, please, on my behalf, say bye to everybody else, because I know not everybody is going to be watching this video, so this is probably the last that you'll be seeing of me. I mean, at least for now. Hopefully someday in the future I'll be back, but as of right now, I have no idea. So yeah, just tell everybody I say hi and bye, and have a good summer. Um, but yeah, so I thought we'll finish off with one more math lesson, still related to trigonometry, and this is something that, I mean, I guess would have been helpful on your final exam, but I gave you the information that you needed on your final exam to do the question without necessarily understanding the question. And this is the question on Euler's formula, where I asked you to prove that e to the exponent I pi plus 1 equals 0. So I'm going to use this lesson to explain to you guys why that's true. Okay, so the thing is, when you write out Euler's formula the way I gave it on your formula sheet, you have e to the I pi plus 1 equals 0. But Euler's formula, it sort of stems from this: e to the I theta equals cosine of theta plus I times sine of theta. And if you have a pi where this theta is, then you have to have a pi where those thetas are. So when you put in e to the I pi, you get cosine of pi plus I, which is the square root of -1, if you've forgotten, I times the sine of pi. And then I told you that cosine of pi is -1 and sine of pi is 0. But if you think about it in terms of degrees, the way we've been working with our trigonometric functions all the whole unit, it doesn't make any sense, right? Because pi is about 3.14, right? Sine of 0 is 0, and sine of 90 is 1, right? So how on earth could sine of what's supposed to be 3.14 be equal to 0? We already know what equals 0, and pi is definitely not the same as 0 up here. So something else is going on. And so the way this works is there's two ways that you can use these trigonometric functions. One is degrees, the way we did all term. The other is with radians. Now, before we can actually do that, we need to learn what a radian is. So basically, the question is, if you have a circle, hopefully that looks all right, that looks fantastic, something like that. Yeah, sure, close enough. So you have a circle of radius r, okay? So you have some radius r, okay? Now, if you start at this point down here, you can pick any point to start, and you draw a line, or a, like an arc along the circle, so that the length of this arc is equal to the radius. That is, if you measured this with a ruler, this would be r. This one would be tougher to measure with a ruler because it's slightly curved, but if you took like a string and you marked off where the string starts, and then you went over there and you marked off where the string ends, and then you straightened it out and measured it across the ruler, you want both of those to equal the same thing, so that this arc is the same length as the radius of the circle. The question is, how many of these segments can you draw before you start overlapping? Like, how many segments does it take to cover a full 360 degrees? Because we know, starting from 0, if you go in degrees, this is going to be 360 degrees. But how many of these radius long arc segments do you need to cover a full circle? And so the way we can break this down is, let's think about one of the previous bonus question on your exam, which was, what is pi? And we said it's the ratio between the circumference of the circle and its diameter, right? That basically, if you rearrange this, if you multiply both sides by d, right, then these two d's would disappear, and you get d times pi is equal to c, the circumference. So basically what this is telling you is that the circumference is the diameter of the circle multiplied by multiplied by pi, right? So you have that the circumference is 3.14159 times bigger than the diameter, okay? But the diameter is just 2 times the radius, right? If I put another radius that way, and I measure that one, if I measure this point to that point, that's just the diameter of the circle. So the diameter is 2 times the radius times pi then, because that pi still carries down, equals the circumference, right? So that means that we can express the circumference of the circle in terms of the radius right here with this r. Now we want to know, if we've got a segment that's this many units long, how many times do we have to go around, or how many of those do we have to add in order to go around the circumference once? Basically, r times what number gives us c, right? That's sort of the question that we're trying to answer here, is that if you've got this segment r right there, of length r, this one segment right here, and you're trying to go all the way around the circle, you're going to have this length r multiplied by some number, which goes from exactly the starting point all the way around back to exactly that starting point. So that's the circumference of the circle, right? So you're trying to figure out the circumference of the circle is r times what, right? That's the question that we have to answer. And if you think about it, you can get that answer from this definition of the circumference of the circle, because we've got an expression right here where the circumference is described in time in terms of the radius, right? So if we just solve for the radius, basically isolate the radius, then that'll tell us what we need to know. And actually, we don't really need to do anything to it. If we just rearrange this a little bit, we write 2 pi, put that in brackets, multiplied by r. I haven't changed anything, right? 2 times r times pi is the same as 2 times pi times r is equal to the circumference of the circle, which is really all the information that we need, right? So what this tells us is that the radius of the circle multiplied by 2 pi is going to give us the full 360 degrees, right? It's going to give us the full circumference. So we've got our answer, that if you take this segment r, and then you draw a second segment r, and then you draw a third segment r, and then another one, a fourth, a fifth, a sixth, and a little bit extra, you'll get to 2 pi, because 2 pi, if you do 3.14 times 2, you're going to get 6.28, something, right? So if you just calculate this as a number, that means a little bit over 6 1/4 of these things are what you need to go all the way around the circle once. Now this arc right here, this arc is special. If you start from the center and then you draw a line to your starting point and you draw a line to the end of the first arc, right in here is going to be some angle, right? Some angle that we would, based on the rest of our unit, traditionally call theta. But this theta is special, right? Because this theta angle is making use of the radius of the circle, right? Normally the thetas that we used, we depended on triangles for it, right? But if you have a straight line here and a straight line there, you don't care if the thing on the other side is a straight line or a curved line, or if there's no line whatsoever. As long as this line is straight and that line is straight, there's an angle in between them, right? I mean, there's still an angle in between them if you have two curves, but it's kind of more complicated to try and figure that out, but you could think of it as there being an angle between them. But here we've got two straight lines, nothing confusing, nothing complicated. You just basically forget about that part and you notice, okay, we've got an angle in here. But that angle depends on the radius of the circle. And so this is a sort of special angle. This angle is called 1 radian. Okay, so this angle theta here is 1 radian. Rad. And it's about, what, like 57 degrees, 57.1 degrees. It's not a pretty number in degrees, but basically what you have here is your theta angle at this point is defined as 1 radian. So basically 1 radian is defined as the angle where if you make that angle's movement in a circle, that if you go from some starting point and you rotate by 1 radian, then the arc length on the circumference of the circle, the arc length that you cover by that rotation is equal to the radius of the circle. Okay, so basically this angle, if this angle is exactly 1 radian, this line is exactly the length of the radius. That's basically what it's trying to tell you. All right? So if this angle is 1 radian, and we can have, 1, 2, 3, 4, 5, I've horribly misdrawn this, but if you can have 2 pi radians all the way around the circumference of the circle, then that means that you can have, so if you have 2 pi of these segments, then that means you have 2 pi of these angles as well, right? You've got 1 radian there, and then you've got another radian there, and then another radian there, and so on, all the way around the circle. It's be like slicing a pizza, right? So what this tells us is that if this angle here is 1 radian, and you need 2 pi of those segments to go all the way around, then you need 2 pi radians to cover that, right? So you've got this whole pattern of 1 radian at a time, just going all the way around. And then this last one, if it's, just what the leftover pieces, because we've got 6.28. So if you've got those sort of leftover chunks there, then it's not going to it's not going to be the exact same angle if you break this up evenly. So don't worry about trying to draw the entire triangle. But basically, what you need to understand from this is that the if this once you've got this angle defined, you know how many of those angles that you need to get all the way around the circle, because you know how many of those arcs you need to get all the way around the circle. So what we know then is that the circumference of the circle, or like to one full rotation, let's say, we know, I'm going to get rid of that, we've got one full rotation in degrees is 360 degrees. We know that, right? To do a 360 on a snowboard or a skateboard is always an accomplishment, right? So 360 degrees we know, but it's also 2 pi radians. Okay? So these are the two different ways in which you could measure one full rotation. But if you notice, the radian itself is this angle here. It's not that arc. That's just a segment of length r. This angle is 1 radian. So if degrees are measuring angles and radians are measuring angles, then that's just two different units for measuring the same thing. It's like miles and meters, right? You could use the same thing, or you could use them to measure the same thing. They'll just give you different numbers. So if you're using your sine and cosine and tangent functions by plugging in an angle on the inside, then that angle should be, you could write it in degrees, or you could write it in radians if you wish, right? So if we've got, let's say, you know, if you look at sine of 90, right? We know sine of 90 degrees is equal to 1, right? But what's 90 degrees? Well, 360 degrees, let's see if we can convert this into radians. So 360 degrees divided by 90 degrees, right? We've only taken 90 degrees of it. 360 degrees divided by 90 degrees, that's 4. All right, so basically we've gone a quarter of the way around the circle if we've gone 90 degrees around the circle. If we started here and we rotate 90 degrees, that's going to be 1/4 of the circle right there. Right? We've gone 1/4 of the circle. So that means that for our radians, then it should also be 2 pi over, you know, some number is equal to 4, right? To make that ratio the same, 360 divided by 90 gives us 4, so 2 pi divided by something gives us 4. If we rearrange this, we can write this as 2 pi divided by 4 gives us our magical answer, right? That we need to plug in there. So if you do the math here, you can leave the pi by itself. You don't have to worry about pi. 2 divided by 4 is the same as 1/2, right? 2/4 is the same as 1/2. If you eat 2 out of 4 pieces of pie, you've eaten half the pie. So that means that you could write this as 1/2 pi, right? Or if you want to simplify it, you can write it as pi over 2, right? So that means that if 360, you know, you could do the same rearrangement here, and you could put 360 divided by 4 gives us 90 degrees. So 2 pi radians divided by 4 gives us pi over 2 radians. Right? So this tells us that 90 degrees is the same thing as pi over 2, that looks like an H, pi over 2 radians, right? That's what we've got. So if I plug in pi over 2 right here, then that means I haven't actually changed anything. If I write sine of pi over 2, as long as I don't put a degrees symbol, because that's different, if I don't put a degrees symbol, you don't have to write rad, by the way. Radians, you usually don't even write anything. You just write it like that. But if I just write sine of pi over 2, that answer is the same thing, because pi over 2 in degrees is 90 degrees, and we already know what that is, right? So you just need to understand the conversion between degrees and radians. So we can, break down some of those. So let's do that. I'm going to get rid of this circle because this is getting a little bit messy. So we've got 360 degrees is equal to 2 pi radians, right? If I just want 1 degree out of 360, I can divide both sides here by 360. Right? And so what this gives me on the left side, this will give me 1 degree, right? But on the right side, I don't touch the pi, I leave the pi by itself. 2 divided by 360, if you just cut out a factor of 2 from each of them, this becomes a 1, so you don't have to write anything with it. And this becomes 180. Okay? So what this is telling you is that 1 degree is equal to pi over 180 radians. Okay? So let me write that down here. 1 degree is equal to pi over 180 radians, right? And I can actually use this to pull out another useful thing. What if I multiply both sides by 180 now? Okay, 180 times 1 is just going to be 180. So this is still going to be 180 degrees over here. And over there, the 180 and 180 are going to cancel out, and I'm going to be left with pi radians, right? And so what this is telling me is that 180 degrees is equal to pi radians, which, if you wanted to get this another way, you could have divided both of these by 2, right? You could have started with our original definition and just divided both of them by 2. 2 divided by 2 is 1, so you're left with pi on that side. 360 divided by 2 is 180 degrees. Same answer, right? So we've got 180 degrees is equal to pi. Now, if you remember from the unit circle, I'm going to have to draw a circle again. Let me move this. So, if you've got your unit circle somewhere there, I hope you can see that. If you've got your unit circle somewhere down here, remember that if you start at 0, if you start, at this point, 0 in the y direction, but in the positive x direction, right? If you've got your axes, your positive x direction is that way, your positive y direction is that way. So if you start at this point, then your coordinates will be cosine theta, sine theta as you go around, right? We talked about this when we were talking about the unit circle. So if your sine theta coordinate is your y direction, then if you haven't moved at all in the y direction, if you're still on the x-axis, let me draw that right there. If you're still on the x-axis, then that means sine of theta is 0, right? And that makes sense. You haven't rotated at all. You haven't rotated any number of degrees. When you rotate this way up to 90, then because the radius of this square, of the circle, because the radius of the circle is 1, then at this point, the point has a coordinates of 0 in the x direction, because it's directly on the y-axis, and 1 in the y direction, right? So there sine of theta becomes 1. Now if you rotate again, so here this is at sine of 90 degrees is 1, and cosine of 90 degrees is 0. If you rotate all the way to 180 degrees, then once again your point is on the x-axis, which means here your coordinates are -1, right? Because you're moving in the negative x direction. And then you're on the axis, so there's nothing in the y direction. So it's -1, 0 for 180 degrees. Right, for an angle of 180 degrees, the cosine of that, cosine of 180, is equal to -1, but sine of 180 is equal to 0, right? And this information is useful to us because we know how to write 180 degrees in radians. So if I just write that a slightly different way then, let me get rid of some of this. So that means that cosine of 180 degrees, well, that's the same thing as cosine of pi, right, which is -1. And similarly, we know 180 degrees equals pi. Similarly, sine of 180 degrees is equal to sine of pi, and we just found with the unit circle that that is equal to 0. So at this point you can hopefully see where we're going, but if not, we're gonna get there in just a sec. So now you can use this information and plug it into Euler's formula. We know e to the I theta is equal to cosine of theta plus the square root of -1, which is I, times sine of theta. Now basically the way this works is whatever you plug in here, you have to plug in here as well. So whatever you plug in for this theta in the exponent, you also have to plug in for this theta and for that theta. So if you plugged in a 2 there, then you'd have cosine of 2 and sine of 2. And this works in radians. All right, that's how you'd use this formula, is you plug in some theta value in radians and have it spit out that answer. So what we can do is if I get rid of, I can get rid of, well, I'll get rid of this stuff down here. The information that we need is this: sine of pi is 0 and cosine of pi is -1. And so what we get is if I plug in pi in place of theta, e to the I pi is equal to cosine of pi, because I have a pi here, so I have to put a pi there, plus I multiplied by sine of pi, right? You can put brackets there if you want to. So cosine of pi plus I times sine of pi. But we know that sine of pi is 0. 0 times anything is 0. So 0 times I is still going to be 0. So this whole term just disappears, because sine of pi is 0, 0 times I is 0. We're just going to have cosine of pi plus 0, so we don't even need to worry about it. We can get rid of it. Now cosine of pi is -1. So we have -1 plus 0 is our e to the I pi. So if we just bring this -1 to the other side by adding 1 to both sides, we get that e to the I pi plus 1, if you've added 1 to that side, equals, and there's nothing left on the right side, 0. So we get this identity that you can use in some math and physics questions, and that's the identity that is often called the most beautiful equation in mathematics, because it's got so many different types of things. It's got the exponential e, it's got Euler's number, it's got pi, it's got an imaginary unit, it's got the real numbers unit, and it's got 0. It's got all of sort of the basic building blocks for so many different mathematical functions, or mathematical expressions or relationships, that it's just nice that they all link together in such a nice way. So that's sort of an explanation of how Euler's formula works, how you can use it to get this answer, how you can use this information, and how you can convert between degrees and radians. If you guys still have it in you at the end of the year, then you can try and figure out what some other angles like 60 and 45 and 30 degrees are in radians, because that way you could make a new trig table, but instead of having 0, 30, 45 on the top, you can have it in radians instead of degrees along the top, and then the rest of the numbers would be the same, but just so that you know what those numbers are. But yeah, so that's it for radians, and that's kind of it for our math class as well. So like I said at the start of the video, it's been a really enjoyable experience for me to be your guys' math teacher. There's so many different things that we could have done. I hope you guys aren't too upset with the things that we decided to do. If there's one thing I can sort of say as like, something that you could consider in the future, is if you find the math scary, just look for a different explanation of it, because there's nothing in all of this stuff, if you break it down to its simplest chunks, it's really not that hard. And I know, as someone who didn't really struggle in math when I was in school, I know that I don't necessarily see the problem the same way everybody sees the problem. But I'm also by no means the best at math, and when in my university math, it's definitely not easy all the time. But for most things, if you just break it down into small enough bits, it's always addition, subtraction, multiplication, division, maybe some exponents here, and then once you start doing calculus, for some of you that won't be for a few years if it happens at all, but once you start doing calculus, the basic kind of bits of calculus are what you end up using. I'm doing third year physics work with lots of stuff. The final answer is like my second and third last steps is just me adding a bunch of numbers together or doing a little bit of multiplication. So it all breaks down to the most basic rules of math. So once you get the hang of addition, subtraction, multiplication, division, which you guys have, get the hang of exponents, 2 to the 6 and whatever, you get the hang of that. You get used to sort of thinking with diagrams. Diagrams can help a lot. So drawing out the unit circle, drawing out the circle to figure out, okay, oh, that's how a radian works. All of that stuff will help a lot. So if these things get confusing, then in future, just try and find another way to look at it. And I'm not saying you have to come up with that way of looking at it, but find another explanation. It could be from a YouTube video. It could be from, something like Khan Academy. It could be from another teacher. It could be from something like that. Try and find another explanation that just breaks it down into the basic chunks. And sometimes the solution is a little bit longer when you start from the basics, but it's easier to understand what's going on. Okay, so in a few years' time, when you guys are getting into the more complicated math, if it starts to stress you out because it's difficult to understand, try your best to break it down. Not everything breaks down as nicely as you might like it to. There are some things that you just have to sit there and learn how they work and grind them out. But for the most part, it breaks down into these basic things that we've talked about. Yeah, aside from that, I hope you guys enjoyed math class this year, and I hope you guys keep your interest peaked for math for next school year. Have a great summer.